The study presented in the sources investigates the depth and mode of ore-forming fluid exsolution from their source. Magmas in porphyry type Cu deposits in the Sanjiang region of southwestern China. These deposits are economically significant ore resources. The research involved the study of 36 magmatic rocks from 6 mineralized systems in this region. Evidence for deep fluid exsolution. The study found that melt inclusions trapped in phenocrysts of mineralizing felsic magmas are significantly depleted in CLS and metals. Petrographic evidence, apatite volatile contents, and mass balance calculations suggest that this depletion was caused by the exsolution of aqueous fluids. These fluids extracted 63 to 97% of the CLS and metals originally present in the magmas. 3 independent geobarometers indicated that all the major phenocrysts in the felsic magmas crystallize within the pressure range of 0.3 to 0.5 gigapascals. According to the authors, these pressures correspond to mid to upper crustal depths of approximately 10 to 20 kilometers. This suggests that the ore-forming fluids exsolved from magmas that crystallized at these depths, rather than from magmas crystallizing entirely within the upper crust or directly ascending from the lower crust. Distance and mechanism of fluid transport. Based on the crystallization depths of the source magmas and the estimated emplacement depths of the Erebites had to transport their metal and S endowments over a vertical distance of approximately 10 kilometers to the site of or precipitation. The study proposes a 2-stage mechanism for this fluid transport. Initially, the metal-rich fluids likely ascended as bubbles suspended in the rising porphyry magmas. Subsequently, most of the ore-forming fluids seem to have percolated through an interconnected fluid network within the porphyry magma at near solidus conditions. The high crystal fractions in the porphyry magmas likely facilitated the development of this fluid network. Continuous input of fluids from the deeper magma reservoir could have maintained the open nature of this network. Methodology. The researchers studied 36 magmatic rocks from 6 mineralized systems in the Sanjiang region. They utilized several analytical techniques. Melt inclusion analysis. Laser ablation. Inductively coupled plasma mass spectrometry was used to analyze the volatile and metal contents of 207 melt inclusions trapped in various phenocrysts of mafic, intermediate, and felsic rocks. Melt inclusions provide a unique way to quantify magmatic, volatile, and metal contents before and after fluid exsolution, and preserve information about pressure and temperature. Most melt inclusions were crystallized, and only unexposed ones were analyzed as a whole. Quantification involves subtracting the contribution of the host mineral. Fluid inclusion analysis. ***17. High salinity brine inclusions were analyzed using LACPMS to determine their CLS and metal concentrations. The contribution of the quartz host was subtracted. The absolute element concentrations were normalized to a salinity of 10 Wt% NaCl equivalent for comparison. Electron probe microanalysis. ****. Amphiboles and clinopyroxene phenocrysts and inclusions were analyzed to determine their compositions for thermobarometry applications. The focus was on shielded inclusions within other phenocrysts to constrain crystallization pressures. Geobarometry. ***3. Independent geobarometers were employed to estimate the crystallization pressures of the phenocrysts in the felsic magmas. All-in hornblende barometry used the composition of hornblende inclusions in quartz and Kiefeldspar phenocrysts. The good agreement was based on hornblende inclusions hosted within other phenocrysts due to potential resetting of unshielded hornblende compositions. 10 quartz barometry used the T contents of quartz phenocrysts in conjunction with reconstructed temperatures and TO2 activities. H2O content of glassy melt inclusions high H2O contents in quartz-hosted glassy melt inclusions provided minimum pressure estimates. Mass balance calculations These calculations evaluated the mineralization potential of the aqueous fluids based on the volatile and metal concentrations in trachydacitic versus rhyolitic melt inclusions and the increase in magma crystallinity between these two compositions. The calculations assumed minimal incorporation of these elements into crystallizing minerals, which was supported by the good match with theoretical trends for 100% incompatibility for most elements except S, U, and O. Study area and samples. The Sanjiang Porphyry skarn, Su. Its metallogenic belt in southwestern China was chosen for this study due to several reasons. The presence of variably evolved magmatic rocks in certain magmatic systems that are clearly cogenetic and contain well-preserved melt inclusions. Existing experimental studies on the evolutionary systematics of H2OS and Cl concentrations in residual melt during high-pressure magma differentiation. Coexistence of melt inclusions with CO2 or H2 or H fluid inclusions in various phenocrysts. The presence of hornblende in quartz phenocrysts in mineralized felsic porphyries, allowing the application of independent barometers. Collected samples included mafic, intermediate, and felsic potassic rocks from various locations within the Sanjiang region, including areas associated with significant mineralization like the Yulong and Beja deposits, as well as prospects and weakly mineralized areas. Implications for porphyry copper deposit formation. The findings of this study support the classical model of porphyry Cu formation, which posits the existence of mid to upper crustal magma reservoirs beneath these deposits from which ore-forming fluids originate. However, the study provides new constraints on the depths of these reservoirs, indicating they were situated at 10 to 20 kilometers in the Sanjiang region, deeper than some previous estimates. The study also suggests that the extent of mineralization is not primarily controlled by the initial metal content of the ore-forming fluids, as the metal content of high-temperature fluid inclusions was found to be similar across systems with vastly different ore-metal tonnages. Instead, the mass of fluid exsolved from the underlying magma reservoirs, likely related to the size of these reservoirs, appears to be the more crucial factor. Furthermore, the different CuO ratios in deposits, despite similar ratios in the input fluids, point to the significant role of selective metal precipitation mechanisms during the hydrothermal stage. The researchers argue against a major erosion level control on mineralization in the Sanjiang region. Strongly and weakly mineralized porphyry stocks occur in close proximity, and the original erebities at Beja and Yulong are largely preserved. The proposed fluid transport mechanisms, involving initial ascent with magma and subsequent percolation through a fluid network, may have broader applicability to porphyry-type Cu deposits worldwide given common observations, such as high phenocryst contents in Sinor porphyries, larger metal tonnages relative to the volume of mineralized porphyry stocks erebity occurrence at the top of porphyry stocks, and the poorly veined and altered nature of the roots of mineralized porphyry stocks. In summary, this research provides detailed insights into the formation of porphyry Cu deposits in the Sanjiang region, highlighting the deep origin of ore-forming fluids and their extensive vertical transport through a combination of magmatic ascent and pervasive fluid flow within crystal-rich magmas. The study emphasizes the importance of large fluid volumes sourced from deep magma reservoirs in controlling the scale of mineralization.
Welcome to the world of geology and earth sciences with Ricardo Vols, a seasoned professional geologist bringing you over 1,000 videos of unparalleled expertise. Whether you're a budding graduate student, an early career specialist, or a seasoned professional, this channel is your gateway to a wealth of knowledge. Explore a vast array of Earth-related subjects, including geology, geochemistry, structural geology, and the application of artificial intelligence and machine learning in geosciences. Stay ahead of the curve with our latest content, covering everything from unraveling the Earth's secrets to exploring global geological phenomena. Subscribe now, hit that like button, and share this invaluable resource with your colleagues and friends. Join our growing community of over 1,800 Earth science enthusiasts and professionals today. Unlock the secrets of the Earth with Ricardo Vols, your top resource for all things geology. The future of geosciences is here, be part of it.
Guys, ever felt lost in geology lectures? Me too. But then I found Systematics of the Magmatic Rocks by Val's Geoconsultant. Trust me, it's like having a study buddy who knows everything. It breaks down complex concepts into bite-sized pieces. Perfect for us postgraduates looking to excel without getting overwhelmed. Plus, real-world examples help solidify your understanding. Nothing feels more satisfying than solving problems confidently. Don't just take my word for it. Grab your copy now and see the magic yourself. Your geological journey is about to get so much easier.
I think these videos are brilliant, and I'm sure you will like them too. Please like, comment, and subscribe, and don't forget to click the notification bell.